undoing this stuff. Okay, so your warm-up today was something we've already done. But you'll see in just a minute why I wanted us to take a look at these. So if we look at the first one, all we're doing is distributing through, and when we distribute, we multiply our numbers, and because we're multiplying like bases, we add the exponents. Check number 1 and see if you have any questions.
Yeah. Oh, wait, actually, no. I was doing each.
Oh,
So that one.
I had it
Okay.
right except for. No. I almost had it. Wait, was this what we did unit 2?
It was.
Wow.
It was part of unit
I don't know how
2.
I disavowed the test. I actually did this right.
Okay. Let's take a look at number 2. Number 2, we're multiplying those two binomials, and the binomials are identical except for the signs. And we kind of talked about the same thing when we were dividing by a complex number. Every time we multiplied something by its conjugate, what happened to the outer and inner terms?
They cancel.
They cancel. So in this one, that positive 10x and the negative 10x cancel. And so this gives us just the first term times itself, which makes squared, right? And the last term times itself, which is squaring, and a negative. All right, let's look at number 3. Here's where we had a binomial squared, and we talked about you could either write it out twice and distribute through, or when we think about Pascal's, it was 1, 2, 1, which means square the first one, because we square that first term, double the product of the two, and square the last one. So if we square the first term, 4x squared becomes 16x squared. If we double the product is negative 4x. Double that, we get negative 8x. And if we square a negative 1, it becomes positive 1. So any questions about that? Square the first, double that product, square the last. All right. Well, today what we're going to look at is factoring quadratics. And I love factoring because it's like math puzzles. One little puzzle after another little puzzle, and they're not terribly difficult.
Didn't we do these last year?
I don't know.
Oh, I thought I remembered something like that.
I don't think so. Did you take accelerated 8th grade year and 9th grade year?
Yes.
You did it 8th grade year. Yeah. All right. So when we factor, whoops, I didn't mean to do that. When we factor quadratics, what does that mean? It means we're going to take an expression, and you could write the whole word if you wanted to instead of part of it like I did. We're going to take an expression, and we're just going to rewrite it as a product of its factors. So we're going to write it as a product, multiplying stuff. All right, we're going to learn a couple different ways to factor this week. Today we're going to look at greatest common factor and 2 of our shortcuts, which are difference of squares and perfect square trinomials. And then tomorrow we're going to look at how can we do any other trinomial. But today we're going to look at basically the greatest common factor and then 2 shortcuts. So greatest common factor, you guys know what that is. That's the biggest number that'll divide into something, right?
Yeah.
So looking at this expression here, 2x squared minus 8x. I'm going to give you just a moment to catch up with me because I can tell most of you are just writing right now. And we'll finish this in a second. Go ahead and copy that down and then we'll talk. Okay, so if we look at this first expression, 2x squared minus 8x. Is there a number that divides into both of these coefficients? What is it? 2. Okay, is there a variable that will divide into both of those? X. So it's the largest number that will divide into all of our coefficients, and then any variables that they all have in common to the lowest degree. Now there's 2 ways I can think about this. I can think of this as 2x squared divided by 2x. What does that leave me? X. And negative 8x divided by 2x is negative 4. Or this is the way my brain works best. I go, okay, what do I multiply 2x by to turn it into 2x squared? X. what do I multiply 2x by so that it becomes negative 8x? Negative 4.
Oh, that is
Okay? So that's how my brain thinks. Alright, let's look at the second example. Okay, so we have bigger numbers here and we have multivariables, but that's not a big deal. Because when we look at this 20 and the 32 and the 12, what is the largest
4.
number that divides into all of those? 4. Okay? Now, what variables do they all have in common? Because they all have to have them in common. An A and a B. Okay, what is the lowest exponent for the A? 1. And what about the B? 1. So this is my greatest common factor, 4AB. Now I'm going to factor that out. So if you guys like the way I do, what do you multiply 4 by to turn it into 20? 5. A is A, B, B. Okay. All right. So what would my next term be? Tell me about the number.
8.
8. Okay, what about A?
A squared.
Any B's?
No.
Nope. All right, last term.
3.
3. Okay, so do you see how we took, in both of these, we took this expression and we wrote it as a product of its factors. We rewrote it as a product of its factors. And we have factored both of these completely over the set of integers. Yes, sir.
Should we put it in standard form or? Like
We don't have to worry about that form so much here. We worried about the form when we started with this and we multiplied it through. So when we factor, we don't have to worry about it.
What's
Okay.
the advantage of putting it into that?
That is a great question. Why would we ever want to factor something?
No clue.
This is why. What we're going to end up doing is taking equations that are slightly more complex than this one, and we're going to try to find, or functions, try to find their zeros. Isn't that where we plug in 0 for the y? Or equation like this. Well, if I have it written as a product, and I want to know when it equals 0, don't I just, one of these factors would have to equal 0. Either this one would have to equal 0, or this one would have to equal 0. So my answers would be 0 or 4. And that's where we're headed with this. We're not there yet. We got to learn how to factor first. And then we'll use factoring as a method to solve quadratic equations. All right. The second method we're going to look at today works when we have a difference of squares. So difference means I'm subtracting two things. And squares here, I'm talking about perfect squares. So when we have a binomial that is a difference of squares, this is how we're going to factor it.
Are those like four-sided problems?
There, I think I have, nope, there. This is the example. This just tells you how to do it, and these are 3 little practice problems.
Okay.
Okay, so let's look at, what do we think? How do we think this would factor? Look back at your warm-up real quick. How do you think this would factor? You got an idea?
Well, I was thinking be A plus B times A minus B.
You were thinking absolutely correctly. A plus B times A minus B. Perfect. Because remember in our warm-up, when we were multiplying those two binomials that were identical except for the signs, that outer and inner canceled, and all we were left with was the first term times the first term and minus the last two multiplied, the first and last. This would give us a squared. Then we'd have a positive AB and a negative AB, which would cancel. And b times negative b is a negative b squared. So when we have a difference of squares, it factors to the square root plus the square root and the square root minus the square root. Because if we were to FOIL this back, if we were to distribute through, we would notice that the negative 4x and the positive 4x just cancel. So all we're left with is x times x, which is x squared, and positive 4 times negative 4, which is negative 16. Okay. Do you think you could do number 2?
Yeah.
Okay. All right. I see some shaking of the heads and no.
Wait,
Let's take a look at what we have here. Is the first term a perfect square?
Yes.
Yes. What am I squaring here?
3.
3n. Is the second term a perfect square?
Yes.
Yes. What am I squaring?
5n.
5n. M. Yes. So it becomes 3n plus 5m times 3n minus 5m. And somebody asked me earlier, does it matter whether I put the plus or minus first? What do you think?
Yes.
No, it doesn't.
No, it doesn't.
This is exactly the same thing. Because when I'm multiplying, guys, is there any difference between 2 times 3 and 3 times 2?
No.
No, that's a cumulative property of multiplication, isn't it? So it doesn't matter whether I put the plus or minus first,
No.
as long as I use different signs. Okay. All right. Is a to the 4th a perfect square?
Yes.
Yes.
Square.
It is a squared, isn't it? Is 81 a perfect
Yes.
square? Yes. It is 9 squared. So this factors to a squared plus 9 times a squared minus 9. You feel good about that?
Yeah. Good.
Are we confident in this answer?
Feeling good.
Are we done with this answer?
Yes.
Absolutely.
No.
Are we?
Are we?
No.
No.
Why?
Let's just
Because
Because
A
it's
squared
not
can
squared.
is A, and then
Look at
9 can go to
that.
3.
That's no fun.
This one factors a little further.
Because you gotta get away to the issue.
So, now the first one, a sum of squares does not factor. There's nothing else I can do with the first expression. But the second factor, a squared minus 9, does factor to a plus 3 times a minus 3. And now, it is completely factored over the set of integers.
Oh, yeah.
Why can you do that with the negative and
Let's try it. Why?
Because it's different.
Oh, I get it.
Okay, to have a square and a plus, they would either both have to be plus. Come on, maybe. So it would have to look like this, or they would both have to be minus, right? And if they're the same, guys, I get a middle term.
Try to simplify it down as far as you can.
that makes sense.
Do you see how I get that 6a that's not in there?
Yes, ma'am.
And so here I would get a negative 6a that's not in there. So there's no way to make a positive 9 here without having a middle term. Okay. Which leads me nicely, you guys are doing great today. My next method is called the perfect square trinomial. And that's what that last one was that you were asking me to do. Okay, so the last one was a difference of squares. It was only 2 terms. This one still has perfect squares, but it's how many terms?
3.
3.
We got this.
Yeah. Okay, so I'm going to go back one page real quick and look at the one you just asked me about. Do you see that if I had a squared plus 6a plus 9, a perfect square and a perfect square? This is a perfect square trinomial. This is also, both of those are perfect square trinomials. And now let's look at how they would factor. This is going to factor to a plus b times,
A minus.
okay, now with
Oh, A plus B.
a plus b. So if we do have that middle term, so is there a more efficient way to write a plus b times a plus b?
Yes.
What's the more efficient way to write it?
A plus B squared.
A plus b squared. And that's what we would want to do. We would want to write it as a binomial squared. We would want to write it as the binomial squared. Okay, so when it's 3 terms, and we notice that first term is a perfect square, and we notice that last term is a perfect square, we're going to try to write it as a binomial squared. What is the square root of x squared?
X.
X. What is the square root of 16?
4.
4. And because this is positive, this should be positive. Because remember when we were squaring binomials, we square the first, we double the product. If I double this product, do I get that middle term?
Yes.
Yes. And we square the last one. So what would this one be, guys?
4x plus 3y.
Okay, if I double this product, do I get a negative 24? No, I get a positive 24xy, don't I? What could I change right here to fix that? Minus. What you're going to notice on perfect square trinomials is whatever the middle sign is the middle. The middle sign is the middle. Now, this shortcut doesn't always work because I'm going to give you one that looks just like this one. I'm going to start it out with x squared and I'm going to end it with 16.
Those don't equal.
But if I wrote this as x plus 4 squared, if I double that product, do I get that middle term? No. There is another method for factoring this, and tomorrow we'll talk about it. This factors to x plus 2 times x plus 8. Yeah? Okay. Any of you who have ever worked ahead in math or might do like a summer skill class or might do Kumon or might do any type of other math, you've probably already seen factoring. So some of you may have been exposed to factoring already. That is awesome. You're just a step ahead of the rest of us. But by the end of this week, we're going to all be champs. All right. This is in your workbook if you happen to have them on page 329. If you don't, then you can write them down just like I did. It is in the green one.
I was feeling.
We won't be back in the blue one for a while.
You can take that home.
Right now?
You can just leave it in your locker.
I don't need the locker. I use it for my lunch.
You left way harder than 6
I just get
Forget
it
about it.
Okay. All right, we have 3 terms here. So maybe it's perfect square trinomial. We always look to see if there's a GCF. Is there a number that would divide into all? The 1, no. Taking a 1 out, would that help us?
No.
No. Do all 3 terms have a variable in common?
No.
No. So there's no GCF. And since it's 3 terms, and I've only taught you perfect square trinomial, let's try that. Is the first term a perfect square?
Yes.
Yes. Is the last term a perfect square?
Yes.
Okay, so let's try to write it as a binomial squared. What is the square root of x squared? X. What is the square root of 9? 3. The middle sign is positive, so we go positive. But you must always double check. If I double this product, do I get that middle term? Yes.
Yes.
Okay. Number 2. Is there any GCF?
No.
Not on this one. Okay, is the first term a perfect square?
Yes.
Is the last term a perfect square?
Yes.
All right, let's try it then. What's the square root of 4x squared?
2x.
2x. What's the square root of 25?
5.
5. and the middle sign is positive. If I double the product, does it give me that middle term? Yes, so it works.
Oh, I'm feeling so good.
Okay. Always the first step, is there a GCF?
Yes.
Yes. What number do they all have in common? 4. Okay, so I can take that out. It's going to leave me 9x squared, perfect square, minus 6x. Let's see if we finish strong. Plus 4. I got a perfect square at either end, so I'm going to try. Okay? So what is the square root of 9x squared? 3x. What is the square root of 4? 2. And that's negative. If I double this product, do I get the middle term? No. So what that tells me is this problem only had a GCF. It does not factor further. Or if it does, it's not a method we've studied yet. Okay, you try number 4 on your own. Okay, did you get 3x minus 2 squared? And this one does work. Yay. Okay.
I got it.
Down at the bottom of the page, these are in the form of difference of squares. But what's wrong with number 7? Is 200 a perfect square? No. This problem does not factor. And when a problem does not factor over the set of integers, we call it prime. Prime is the answer we use when it does not factor over the set of integers. Okay, I'm going to skip number 8 just because of time. And I want to look at number 9. Is 36s squared a perfect square?
Yeah.
Is 4t a perfect square?
Yes, it is.
Okay, but did it have a GCF I should have dealt with first?
Yes.
Yes, it does. GCF always first. Don't get ahead of yourself. So now is what's left still perfect squares? Is the 9s squared a perfect square? Yes. And the 1 is a perfect square, so it factors to 3s plus t and 3s minus t. This is a terrible problem because my t's look like pluses and my s's look like 5s.
With a little eye
But, all right, your homework is out of your textbook, the geometry textbook. And it's on page 484. It's numbers 14 through 19 and 21 through 35. Enjoy your factoring puzzle homework.
I love